Hello everybody, my name is Joanne. If you wanted to know how I look like, this is exactly how I look like. It's an accurate description. So today I want to hopefully turn a Boolean expression into a circuit. Hopefully I'm able to help you in that area if you need to. But before we get to that, I want to talk about logic gates because we have to go through the basics before we get to the big picture. So with logic gates, there are three common ones. But before I get to that, does anybody know why exactly we need to create circuits? Well, circuits, when engineers design circuits, they need to have a way to explain the behavior of that circuit, and so they do that with logic gates. And if I can just move this along. Now, these are our logic gates, but before I want to explain a little bit about it for each of them. Now, as I said before, there are three common Boolean operators, which is your AND, your OR, and your NOT. Now, the truth tables for the AND look like this. If I have two inputs, like X and Y, then we use 0, 0, and our outputs, we just multiply these two inputs and we get a 0. Now, why in the truth tables do we use binary numbers? The reason for that is 0 is used to represent as false. 1 is used to represent as true. And as you know, computers, they use binary numbers to communicate, or, that's kind of like their number system. For us, is just the decimal form, but for computers, it's just binary numbers. And with binary numbers, the computers are able to add, subtract, and all that good stuff. So back to the inputs. If we had x as 0 and y as 0, as I said before, you multiply these two numbers together and you get 0. Fair enough. Now, if we have x as 0 and y as 1, obviously 0 times 1, you would get 0. And here for your inputs of x, if x is now 1 and y is just 0, well, either way, your output's still going to be 0 because 1 times 0 is the same as 0 times 1, which would be 0. Now, you multiply x times y, and x in this case is 1, and as well as your y is also 1, and you would get 1. Simple enough. Now we go to our ORs. Now our ORs, our outputs, they don't exactly multiply, but they add. So if your x is 0 and your y is 0, well, add those two together, you get 0. Here, if you get x as 0 and your y as 1, add these two together, you'd get 1. Same here, you would get 1. 1 plus 0 is 1. But here, obviously, you would think, x is 1, y is 1. Well, you get 1. But you say, well, 1 plus 1 is equals to 2. But in this case, this isn't binary. So this isn't in decimal form, as you would like to think, but this is all binary. So x says 1 plus 1 would get you 2, of course, but convert 2 into binary, and you would get 0, 0, 1, 0. Now you look at your NOT and your NOT gate, which is another common one. And here, your x is just 0, and your output is just 1. I would like to point out that I've seen this throughout the semester, and your input x is x, but your output is not just x with apostrophe, it's just x prime. That's how you say it. So if you might want to know that for reference. So here, you're just taking the opposite of whatever your input is. So the opposite of 0 here is just 1. Likewise, the opposite of 1 is just 0. In my opinion, this one's my favorite because these are the least you have to memorize ever. So here you have, I want to explain this a little bit. It's just your exclusive OR. Here your input are x and y, and your output is just x with a plus and a circle around it, y. That's how it's different from x, XOR to OR. So if you look at here, inputs are 0 and 0, and your output is 0. Here, what an exclusive OR does is if you have a different combination like of binary for your input, like 0 and 1, then it comes out true. In this case, I want to rephrase myself and say that, by noticing this pattern, at least one input must be true, at most 1. Because if you notice, your x input here is just false, is 0, I mean, and y is just 1. So if at least 1 is true, then your output is true. Here, if x is 1 and your y 0, comes out 1. But here, 1, 1, obviously you would say, okay, one of them is true. You would think you would get true, but no, you would get false, because both of these, I said at most 1. And so that's how it looks like. And here, these are how your gates look like. These, of course, are your inputs here, and your output is just x, y. Same here. I'd like to add another way to remember that this is an AND gate is, if you look at this gate, it's kind of like the shape of a D, like a capital D, like the end of the word AND, like the letter at the end of this word, AND. So that's one way of remembering. And here your OR, now it is a curve here, like this. It kind of looks like a boomerang, if you want to think about it. But yes, that's what an OR looks like. And this is what your NOT looks like. Your NOT, your input here is just x, and then you have this triangle here, and a circle here, and your output is just x prime. Now your exclusive OR is just 2 inputs here, if I can get this right, your x and your y, and then you have a curve here, and then you have one like crest of a moon, I want to say. It kind of looks like that, but it's kind of like your OR, but with just another curve behind it. So it kind of looks like this, because there we go. Your input would just be x and y, and of course your output is just x. There you go. X with a plus and a circle around it so that you don't get confused that it could be an OR. So in this case, I highly encourage you to memorize that the plus here is your OR, and your AND here is to multiply. Now, I told you one shortcut of one way of remembering that the AND gate is just, the D-shaped thing over here, just like the letter of the word AND. That's one way of remembering it. And these right here are your truth tables. Now, you will come across the opposite. Like since we discussed here, your AND, if I can get it back, okay. Your NOT gate, essentially the And essentially, the gate, if you notice, it's kind of like a triangle with a circle on it at the end. That's your not. But if you were to take your and you were given like the opposite of and, would just be called your NAND. If you think about it, it's kind of like they took the word not and together, and they made the word and, NAND, sorry. So that's one way of looking at it. And your gate for that one is just this D. Of course, you would get it and. Now, you got to input the not part. So that's just this circle right here. And that's it. And that is your NAND. And now your NOR, if you can remember, well, essentially what that is just your not, or, and, okay, let's just take this one, your or. Everyone knows what that looks like. It's just the one with the curve like this. There we go. And you're not. If you can remember, all we did here is just add a little circle on it. Well, guess what? We're just going to add a circle. That's your output. These are your inputs. And that's pretty much it. So, but your truth tables for this one, it's kind of like if you took your truth tables for here, your truth tables for this NAND right here, this AND, all you have to do is take the opposite of your output here in AND that's your truth table. So for NAND, put this in, your NAND is just, you know, the x times y prime. All of this is prime. So just take the opposite of 0. It's just 1, 1, 1, and 0. Because the opposite of 0 here is 1. Same here, and the opposite of 1 is just 0. Same thing goes for your ORs. You just take the opposite. When it comes to NOR, here you get 1, 0, 0, 0. It's simple as that. So here I want to discuss a little bit about Boolean expressions. I do want to tell you that the inputs don't necessarily have to be 2 inputs. You can have 3 inputs. You can have numerous amounts of inputs. So that's one thing you have to remember. That is not just, so if you see like 3 letters, you're like, oh my goodness, what do I do? Well, it's okay. You can have you can have more than 2 inputs. I just use the truth tables because it was for 2 inputs because it's just less stressful. This one is a pretty long Boolean expression right here. Should have started out with a simpler one, but that's all right. So in this case, you are presented with an input. Like in this case, my one suggestion is to start little by little. Of course, you look at this and you're like, oh my goodness, that's a lot. But let's just start with one by one. Here, as you can see, you have an A and B prime. Now, B prime, as you know, is just a NOT gate. So let's start out with A and B. Let's just say you have, obviously your output, your inputs would just be like this. And so if you notice B, there's nothing going on really much with A. It doesn't have, it doesn't have a prime on it, so you're okay with this. Except here, B prime, well, B prime is just if you looked back at the truth tables, B prime is just the opposite of B. And here we are presented with B. So how do we make it the opposite? Well, make it your NOT gate. And there you go. You have B prime now. Now here, what is A and B prime doing? Well, here mathematically, they are multiplying. And to represent a multiplication, you would use what exactly? You would use your AND gate. Because remember, AND gate, you are multiplying two inputs together. So, here you go. There you are. And of course, you have your output. Now, you have C, and C is a different one, so let's put C right over here. Now, in C, it isn't prime, so we don't have to worry about that. So let's bring that all the way over here. Now, my one question is since A and B prime here that we have is your AND gate, well, what is this plus? This plus translates to what logic gate? It would be your OR gate. So you have it right here, your OR gate. And there you go. Now, before we get a little bit ahead, now you look at this entire thing right here. You look at A times B prime plus C. Now, that's in parentheses, we did that. But what's outside of the parentheses is what matters. It's your prime. So essentially, all of this that you created is prime. So how do we do that? Well, we just add a little circle, which is your NOR gate. And now, since we're done with this parentheses, well, with this one at least, we have your D. Now let's go down here, bring D, and let's bring that all the way over here because there's no D prime here, so it's not like you have to make it a NOT gate. So here's your D. Funny pun. And so let's bring that out. This is your NOT. We want to connect these two together. Now, how do we connect these two together? Well, all this is being multiplied times D. And so when we say that both of these are being multiplied, what logic gate do you use? Well, if it's multiplication, you would use your AND gate. So here you go. Here's your AND gate. Alrighty, now that we're good here. Now, let's focus on this one right here. Now here, we want to come down here separately. We're working this like parentheses, parentheses by parentheses. So here you have your C. So let me get this in order. C. And your D here, because that's what we're given. Now C times D. Again, times would just be your AND gate. Now, since we said over here that this is being multiplied, what is happening up here? See, now you have a prime. So C times D prime. So just make this a NAND gate. Because essentially what the prime always does is just whatever you multiply here, you take the opposite of that. So it's your NAND gate. Now we have B here. Your B, which is your input. So B here, it's not prime, so we're okay here, we're good to go. So let's just come across over here. Now my one thing is that you see that how this whole thing is being added, plus B, and we need to connect these two right here. So with addition here, what do we essentially have to do? What logic gate would you use if you were given x plus y? Well, x plus y, your logic gate there is just your OR gate. There you go. So, bring this out here. And you see your A here. Well, all this is being added plus A. So all this plus A, you would use your, which logic gate would that be? So here I'm going to put A here. What logic gate would you use if you're just adding? Again, you would just use your OR gate. Now, we're done with these two parentheses here. This parentheses right here in brackets, this represents this one right here. And this one right here is this whole thing. But now, like this Boolean expression, we have to join it together. And this plus sign with the circle we have seen before. So this plus sign with the circle is what logic gate? It's your exclusive OR. So you bring these two together. Great. Now your exclusive OR, how would we represent that? Well, is just this curve and then this other half moon thing going on here. Now, since we have it as that, but now look at the bigger picture now. Since we have already connected these two, but now is just the opposite of all of this because you see this prime out here. So this prime out here, your exclusive OR turns into your NX OR, which is just a circle. And that is your input and output. Now here, we did the whole thing. We are done. Now, I want to apologize because I might have confused myself. When I was done creating all this C, you don't have to create another C. You could just bring down this C right here and just connect it like so. So then you wouldn't need this C anymore because you're bringing it down from here and you're connecting it right there. Likewise with D, this D right here, you can, you can connect it from here there you go, and that's your D. B, well, B here you can do the same. But first I kind of want to do A. With A, you can do this and bring it all the way over here. And with B, you can take, I believe, this part connect it right there. And so essentially what you'll have is just, you don't have to have this C right here because you're bringing the C down here. And what is it? And so now that is the that is the solution of this Boolean expression. You turn it into circuits. And that is essentially what that circuit looks like when you convert it from this to all of this. So circuits, they can look differently from others. It doesn't have to be a one-way answer. You can have multiple circuits and they do essentially the same thing as this. So in a way, you can have, there is no like this is the absolute, like this is what exactly the circuit of this should look like this is the way that it should look like. But no, I'm here to tell you that there are different ways to make other circuits. So if your circuit looks different from another person's and you think it's right, then go with your gut instinct. So, or you could use a truth table and then go through all of this by implementing that truth table to see if this corresponds to this. I do have one more problem to go through, and I swear that this will be the easiest one that you'll have to encounter. But yes, I want to go through one more to see if you actually understand. Should have started with this at the end, but